Have a look up at the board right now. What do you see? What do you see on the front whiteboard right now? Clicker? Yeah, these are condensation trails from aircraft, right? Call them contrails sometime. What do you know about these condensation trails from these aircraft? Tell me something about this airplane that left this condensation trail. Pardon me? It's a jet? Okay, so it's got a jet engine. It's not a propeller-driven plane, probably. What else do you know? It's got two engines? Okay. Okay, so this one right here has two engines? I should do that in another color. Two engines because you see two condensation trails right there. What else do you know about this airplane? It's moving, yeah. In fact, we can, that seems like such an obvious thing, but that's important, okay? We want to identify even the obvious things. It's moving, and I think we can even identify which way it's moving. I think it's going this way, because the contrail you can see gets a little bit wider here, just a little bit wider up here than it is here. So I think it's moving kind of down and to the right. What else do you see? The one in the back was recently. So this one was here recently? Or this one? Okay, so there's two of them. So there's two airplanes. There's the one on the front and the one on the back. There's a condensation trail right here that looks like it's going this way. There's this one which looks like it's in the back, and it was, what did you say? It flew by pretty recently because the condensation trail hasn't had a chance to spread out yet. This one was a while ago. So we got the fact that it's a couple airplanes. We know the direction of those airplanes. We know that there's two engines, at least two engines on this one, and probably on this one as well. We know how recently, roughly, they flew by. Okay, we know that they're both moving. Okay, we know which way they're moving, and so there's a lot of things that we know about this, right? We've never even seen the airplanes. In fact, I never even told you these were airplanes. Okay, Rucker first said that it was a condensation trail of an airplane, and then we went from there. You guys told me everything, right? And we've never even seen the airplanes. We've indirectly observed some of the properties of these airplanes without ever having even been told that there's airplanes here. The point that I want to make with this, guys, is this. Okay, there are subatomic particles, protons, neutrons, and electrons. There are, in fact, even what I sometimes call sub-subatomic particles, because although electrons we still consider to be fundamental particles, protons and neutrons we don't. We now know that protons and neutrons can be broken down even further. The thing is, we can't see them. So how do we observe what makes up protons and neutrons? Well, we have to observe what makes up protons and neutrons indirectly. Now, there's a couple of ways that we can observe what makes up these protons and neutrons, okay? And it primarily involves, well, both methods primarily involve brute force smashing these things apart. Okay, in the end, you got these protons. You want to find out what's inside a proton? What does a guy do when he wants to find out what's inside something? He breaks it. He breaks it, right? There's a lab called the Large Hadron, it's called CERN, that has built this particle collider called the Large Hadron Collider, which, by the way, was down for 2 years. Okay, doing maintenance on it and improving it for 2 years, and it's just came up and running again sometime in the last week, literally. And its purpose is, it's huge. It's something like 30 kilometers in circumference. It's massive. Its purpose is to accelerate charged particles to this unbelievably high speed, 99.99 something like that percent of the speed of light. Like unbelievably high speed. And then smash them into each other, break them. That's it. You spend billions and billions and billions of dollars. It's the world's most expensive machine in the history of the world. It's the most complicated machine in the history of the world. And its purpose is to accelerate things the size of protons to really, really high speeds so we can smash them into each other and break them. In the end, you get two cars in a parking lot going at 6 kilometers per hour and they accidentally hit each other. What happens? There's a fender bender, right? Maybe somebody's car gets dented, maybe somebody's car gets scratched, but in the end, it's not that much damage, right? You don't find out what's inside this car by smashing them together at 6 kilometers per hour. But if you get two cars going on the highway at 110 kilometers per hour and they happen to hit each other head on, what happens? The cars pretty much disintegrate, right? Pieces fly all over the place. So we can find out some of what makes up the car. Hey, there's a bolt over there. I didn't know that car had a bolt like that. We've just observed the composition of the car by breaking the car. And how did we break the car? We didn't just collide them into each other. We collided them at really, really high speeds. That's what we got to do. Just hold on right there, okay? That's what we got to do here, guys, to observe what makes up protons and neutrons and that kind of thing here, John, is to accelerate these particles to incredibly high speeds to overcome the forces that exist within them. To overcome, in the case of the cars colliding, to overcome the welds between this piece of metal and this piece of metal. To overcome this bolt, this force of the bolt that joins this to this, and so on. Okay, we have to overcome those forces with a lot of energy, and that's what we do. Except the energy here comes from getting them to not 110 kilometers per hour, but 99.99% the speed of light. Smash them into each other, break them apart, and then see what's inside. So how do we see what's inside? Well, that's where this comes in. We can't observe directly what's inside. We're not even talking about protons. We're talking about things that are smaller than protons. So there's a couple ways that we can do that. Okay, one's called a cloud chamber. A cloud chamber involves, look, you smash these things together, and then inside this cloud chamber, you indirectly observe what comes out of this collision. The cloud chamber consists of this dust-free air, so it's kind of purified air in a sense that it doesn't have any impurities like dust or particles like smoke or dust or anything like that. But it's super saturated with water or alcohol. So it's basically ready to rain water or alcohol. Like, you know how you go to the zoo and you walk into the, I forget which exhibit it is. It's like a rainforest exhibit or something. And you walk in there and it's so unbelievably humid. You guys know which one I'm talking about? Like it feels like it's ready to rain. It's so humid in there. That's kind of what we're talking about here. The dust-free air is super saturated with water or alcohol. Now, the charged particles, these charged particles, by the way, are the products of this collision. It's not the proton. It's what makes up the proton. It's the components that we're trying to observe. These charged particles ionize molecules in here. So the bolts that are flying off the car, okay, the little charged particles that are coming out of the protons, ionize molecules. And then these ionized molecules cause the vapor. Okay, remember we got a gas, but almost a liquid. It's almost condensing. It causes the gas, it causes the vapor to condense. And it forms cloud, right? It forms a cloud, hence we call it the cloud chamber. This is what you see, basically. The condensation caused by these ionized molecules going through this supersaturated gas. Okay, this is what we see. And we follow these, and we observe these things, and we determine, just like we did as a group a few minutes ago with the contrails following the airplanes, we come up with some of the properties of what caused it without actually ever having seen what caused it. So, dust-free air, supersaturated with water or alcohol, charged particles that come out of the collision, ionized molecules, and they cause the vapor, because that's what we had, it was gas, right, cause it to condense. Okay, and then we follow this condensation trail or this cloud trail. Now, the bubble chamber is kind of the opposite of that. Okay, in this case, we have not a gas that's almost a liquid, but we have a liquid that's almost a gas. We've lowered the boiling point of this liquefied gas to a point that's just above the temperature that we have. So in other words, it's almost ready to boil. This was almost ready to condense. This was almost ready to boil. Now, when we collide these protons or whatever, and the things come out of them, these little charged particles, the bolts come out of the car as you collide the car. These charged particles ionize molecules, just like they did in the cloud chamber. But this time, instead of these ionized molecules causing the vapor to condense, instead of causing the gas to become a liquid, this time it causes the liquid to become a gas. So it's causing it to boil. instead of following the cloud behind it, we're going to follow the bubbles behind it. When it boils, it causes bubbles. When it condenses, it causes clouds. In the first case, we can follow the clouds and observe some of the properties. In the second case, we can follow the bubbles and observe some of the properties. Does that kind of make sense? What might we expect to see? Well, I said kind of like this, right? Except it usually is a little bit more complicated than this. This would be an actual picture from a cloud chamber. There's stuff going everywhere. Straight lines, curved lines, circles, spirals, and so on. Okay, in the end, it's not enough to just observe that these things were going in a straight line. What do we want to do? Let's add a magnetic field. Let's add an electric field. Let's add a lead barrier to slow these things down. Let's add all kinds of things. If we add an electric field and they speed up, well, we know what charge is, whether it's positive or negative, right? If we add a magnetic field and we measure the radius of the path, then we can determine maybe how fast these things were moving, maybe what the charge of these things were, okay, and so on. So we can look at kind of a simplified version like this and say, well, there's two of them and two engines and so on. But if we add things to this, okay, like magnetic fields and electric fields and barriers and so on, then we can determine even more. In fact, sometimes even numerical values of things, calculations of things. Does that kind of make sense? So that's how we observe these particles that are smaller than protons and neutrons. The particles that I sometimes call the subatomic particles. But what are these subatomic particles? What are they? Like, what are the actual particles? What are they called? Here's the table, the chart that you don't have in your notes that I'm going to ask you to copy, but it goes pretty quick for us here. There are two basic kinds of particles. I'm going to write down in blue a whole bunch of stuff. I'm going to write down in red what you have to remember. Now, why am I giving you more than you have to remember? For perspective. If I just write down the details that you have to remember, it's not going to make any sense to you. You might remember it, but it won't make any sense. Okay, so remember, blue, okay, is perspective. Red is details that you have to know. So these particles can be broken down into two categories, fermions and bosons. Bosons are force-carrying particles. You guys may have heard of a particle called the Higgs boson. Okay, it was just recently discovered within the last couple of years by this Large Hadron Collider, Switzerland and France. Basically, it's the particle that has been hypothesized for years and years and years, but never actually observed until we had the technology to observe it. It was thought to be responsible for mass. This is why we have mass. Okay, now we've observed it, so we're pretty sure that that theory works. Okay, fermions are the kind of particles that we want to focus on here, okay? We're going to break down fermions into two subcategories, leptons and hadrons. Leptons, I should say, are particles that are not mediated by that strong nuclear force. Remember we talked about the strong nuclear force when we were talking about radioactivity, particularly when we were talking about alpha decay. Okay, when you got protons repelling protons by the electrostatic force, but protons and neutrons attracting each other by the strong nuclear force. Okay, leptons are mediated by the strong nuclear force, hadrons not affected by the strong, sorry, the other way around. Hadrons are affected by the strong nuclear force, leptons not affected by the strong nuclear force. Now the leptons are the simplest things because they're the particles that are fundamental already. An example of a lepton would be an electron. Doesn't get any smaller than an electron. We have to know about the electron. Another example of a lepton would be the electron neutrino. Now we've learned about these electron neutrinos already, although we only called them neutrinos. We didn't call them electron neutrinos. But when we were talking about neutrinos in the context of beta plus decay, we were talking about electron neutrinos. What other kind of leptons do we have? Well, we have muons, but you don't have to really know about those. We have muon neutrinos. We have the tau, and we have the tau neutrino. Don't need to know about those either, really. Plus, we have the antiparticles. What would be the antiparticle of an electron? You guys know this. What's the antiparticle of the electron? The positron. What's the antiparticle of the electron neutrino? No. The electron antineutrino. We'll just call it the electron antineutrino, or oftentimes we just call it the antineutrino. The antimuon, the muon antineutrino, the anti-tau, the tau antineutrino. Okay, these are the ones that we're really concerned with, though, is the electron and the electron neutrino, which is the only neutrino that we've learned about, and then the positron and the electron antineutrino. Those are fundamental particles. As far as we know, it doesn't get any smaller. It doesn't get any more fundamental. And it's kind of ironic, you know what? The first fundamental particle that was observed was by Thomson in 1897. It was the electron. The first fundamental particle observed, we still believe to be fundamental. All the other ones, protons, neutrons, that were discovered later on, thought to be fundamental. Hey, now we don't think they're fundamental. In fact, now we know they're not fundamental. Hadrons are mediated by the strong nuclear force. Hadrons are made up of quarks. Quarks are fundamental. Quarks are as small as it gets. Now there's examples, 6 examples of quarks. There is the up quark. And there's the down quark. There is the top quark. There is the bottom quark. We're concerning ourselves with the up and the down, because that's what makes up protons and neutrons, is the up quark and the down quark. But there is also the top and the bottom. There's the charm quark. And if you think these names are getting really strange, okay, the up, the down, the top, the bottom, the charm quark, if you think they're getting really strange, they get even stranger. Okay, the last one is the strangest name of them all, literally. The last quark is called the strange quark. Plus the antiquarks. The anti-up quark, which you'd think would be the down quark, but it's not. The anti-down quark, which you'd think would be the up quark. The anti-up quark, by the way, is that quark that you use when you're playing Texas Hold'em, right? The anti-up quark, you have to anti-up. The anti-down, the anti-top, the anti-bottom, the anti-charm, the anti-strange. Apparently the anti-funny as well, because it didn't go over very well. Now, I'm going to put in green one more little thing, and that's the charge. The reason I'm putting it in green is because you have to know how to deal with a charge, but it's on your data sheet. So you don't need to memorize the values of the charge. You got to memorize what's in red. Blue is perspective. Green, you got to know, but it's on your data sheet. Make sense? I want you to have a look at this last page, literally the last page of Physics 30 notes for the year. We're going to look at beta decay in terms of these quarks. Because remember we said what beta decay involves. Beta negative decay involves a neutron splitting up into a proton and an electron. How does that happen? Okay, how does that happen? Well, we're going to look at it a little bit more fundamentally right now. What about a positron splitting up into a neutron and a proton? Okay, again, how does that happen? We're going to look at it more fundamentally right now. Just drop your pens for a second. I'll give you a chance to write this down in a second, okay? UDD stands for up, down, down. These are our quarks. These are the quarks, that is, that make up protons and neutrons. There's other quarks as well, but the ones that we're concerned with are the up and the down. Okay, an up quark has a charge of 2/3. A down quark has a charge of -1/3. And a down quark, another down quark, has a charge of -1/3. When we add those charges up, 2/3, -1/3, -1/3, what do you get for a charge? 0. What is this? If the charge of this is 0, what is it? It's a neutron. An up, down, down. Well, an up is 2/3. An up is 2/3. And a down is -1/3. When we add these up, 2/3, 2/3, and -1/3, it gives me 3/3, right? Or a charge of 1. What has a charge of 1? A proton. Plus, what's this? Plus an electron. Plus an, no, not a neutrino, but you're close. Yeah, neutrino, electron, neutrino, doesn't matter if you mention that word electron in front of it. Anytime we're dealing with the neutrino, it'll be the electron neutrino. But this isn't the neutrino, this is the anti-neutrino, right? This is beta negative decay, when a neutron changes into a proton and an electron, and it can do that because a neutron is not a fundamental particle. The bottom one here, what do we got here? Well, UUD. UUD is U is 2/3, 2/3, and -1/3. We add those up, it gives me, what's that give me? +1. That's going to be a proton, right? What's a UDD? That's going to be 2/3, -1/3, -1/3. Adds up to give me 0, which is a neutron. Look, a proton changes into a neutron, and what's this? What's E plus? What is it? No, positron. Plus a positron and a neutrino, an electron neutrino or a neutrino. Now, take a look at this, guys. Hey, this isn't really something you got to be familiar with, but the reality is beta plus decay. This is beta minus, right? This is beta plus. The reality is beta plus decay is kind of a two-step process. Actually, we never talked about that, and you don't really need to know about that. But the reality is, in beta plus decay, you get a proton decaying into a neutron, and then what we call a virtual particle. And then that virtual particle, in turn, decays into a positron and a neutrino. Okay, as far as you're concerned, it's okay just to assume that the proton decays directly into the neutron, the positron, and the neutrino. But it's really two steps. Okay, there's this virtual particle that's in between that. Does that make sense?